is if we have a function y equals f of x. In this case, we're going to let the independent variable be t. So if we plug this back into the equation we have up on top, we get y equals f of t. So our parametrization here, we can write as x, which is t, then y, which is f of t. So a concrete example of this would be, let's say we have y equals sine x. So I'm going to let my parameterization be t, comma, sine t. So that gives us a parameterization of a function. We can have the same thing if the role of x and y are switched. So let's say we have x equals a function of y. Same idea is going to hold. I'm going to let my independent variable, I'm going to let my y take on the value of the parameter. And if we plug this back into the equation we have up on top, we get x equals g of t. So putting these together, this tells us that the parameterization we have in vector form will be g of t, comma t. A specific example of this might be, say we have x equals y squared plus 4. Since y is the independent variable, we know that y will be t. If we plug t into the equation, we have x equals t squared plus 4. So putting these together in vector form, we see that our parameterization r is t squared plus 4, comma t. Now there's one complication that can come up on these, and that is if the curve is parameterized sort of backwards. So let's say we have the curve y equals x squared. But the arc we have in particular, let's say, spans out this section of the curve here from 2, 4 to 0, 0. So t is not going to increase from the vertex out to this point over on the edge. This will correspond to t equals 0, and by the time the curve ends, we are here. So because this is parameterized backwards, that tells me that my t value is going to go from 0 up to, well, we'll leave this blank for now. I notice that the x ends at 2, or it starts at 2 and ends at 0. So x starts at 2, ends at 0. So what we can do here is, normally we would say, since x is the independent variable, normally we would say x equals t, and then y equals t squared. But this will trace the curve out in the wrong direction. So what we'll do here is let's replace all of our t's with, well, we want this to start at 2. So we'll make this 2 minus t. This way we're also going to have x equals 2 minus t. And if we plug this into the y curve, we get y equals 2 minus t squared. Now the question is, well, where should this end? For what time value? And I want this to end when both x and y are 0. X will be 0 when t is 2. So this says we can rewrite our parameterization as r of t is 2 minus t squared, and this will hold as t goes from 0 to 2. So that's the first complication that can arise on these. The next type of problem that we'll look at parameterizing is a line segment. So we looked at functions. Let's look at line segments. So most line segments you can write as a function, but it can sometimes be quicker to use what is called a convex combination. The idea here is that r, we can write this as t times the endpoint, and we're going to treat that endpoint as a vector, plus 1 minus t times the starting point. We can think of this like a vector. You might notice what happens if you plug in 0. R of 0, this whole first term is 0 times the endpoint, which is 0. If you plug in t equals 0 to the second term, we get 1 times the starting point, which tells us that at t is 0, we are at the start point. And then look at what happens at R of 1. If we plug 1 in here, I notice the entire second term will be 0. And when t is 1, we're at the endpoint. So this gives us a convenient way of parameterizing a line segment if we know the starting point and the ending point. So let's look at an example. Let's say we want to come up with a parameterization for the line segment, for the line that runs from 2,4, say, to 5,3. So I can say R will then be t times the endpoint, which is the vector 5, 3, plus 1 minus t times the starting point, the vector 2, 4. If we distribute t through the components and distribute 1 minus t through our components here, we've got 5t, 3t, plus 2 minus 2t, 4 minus 4t. And then if we combine these two vectors together, if we add the x components, we get 2 plus 3t, and then 4 minus t. And as a quick check, if you plug in t equals 0, we're starting at 2, 4. That's good. And if you plug in t equals 1, we're at 5, 3. So at t equals 1, we're at the endpoint. So this is a quick check to make sure we've done this correctly. So that is line segments. So functions and line segments combined together will cover 90 to 95% of all parameterization problems you'll come across. There's two more things that you might see, and those are both conic sections. By far, the more popular would be a circle or an ellipse. So remember, if you have an ellipse, this is of the form x minus h squared over a squared plus y minus k squared over b squared equals 1. And if you think of some trig identities, in particular, the Pythagorean identity says that sine squared t plus cosine squared t equals 1. So it turns out the order doesn't matter here, but the more conventional way to do this is to pair the cosine with the x. So if we think of these as being equal to one another, this says that cosine squared t should equal x minus h squared over a squared. And for our second term, these must be equal. So sine squared t should be y minus k squared over b squared. And now let's solve each of those for x and for y, respectively. So we'll start out by taking the square root of both sides and then multiplying the a over. So we get a times cosine t is x minus h. And then finally add the h to both sides. So we get x equals a cosine t plus h. And we're going to do the exact same strategy for the sine term. If we square root both sides and multiply to get rid of fractions, we get that b times sine t is y minus k. Solving for y, we have y equals b sine t plus k, which means our final parameterization here for any ellipse will be r equals a cosine t plus h, b sine t plus k. Let's look at a concrete example of this. So suppose we have, we're given the ellipse. Maybe we'll have a sketch of this ellipse. So they tell us that the ellipse has a center that's 1, 2, and our radius in the x direction is 3, and in the y is 4. So based on this picture, all the stuff that is going with the x, I see that our center for the Our x component of the center is 1, so that's h. The y component of the center is k. The radius in the x direction is 3. And then the radius in the y direction is 4. So if we plug all of these in, we have that r is equal to 3 cosine t plus 1, and then 4 sine t plus 2. A little note on here is that on the previous problems, the value of the parameter for our line segment was 0 to 1. For an ellipse, if you think of a unit circle, our angles are going to go from 0 to 2 pi. So this covers 99+% of problems you'll have to deal with. There is one more thing that you can see this sort of as a bonus topic, so if you want to stop now, feel free. Otherwise, our last conic section will be the hyperbola. So if you recall, the hyperbola is of the form x minus h squared over a squared minus y minus k squared over b squared equals 1. It looks very much like the parabola, the ellipse, but instead of a sum, we have a difference. So once again, to parameterize this, we're going to think in terms of the trig identities. This one is a little less fluently known by most students, and this is the secant tangent identity. We have that secant squared minus tangent squared is equal to 1. So we're going to do the same thing we did in the previous problem. So we're going to say that if this is the case, then these terms should be equal. So this says that x minus h squared over a squared should equal secant squared t. And likewise, the subtracted terms should be equal. So we have that y minus k squared over b squared should equal tangent squared. So solving each of these for x and y respectively, we have that x minus f, we take the square root of both sides and then multiply the fraction over. So we have that x minus h equals a secant t. For the other term, we have y minus k equals b tangent t. And then finally, solve for x by adding the h over. So we get x equals a secant t plus h, and y is b tangent t plus k. So this gives you a way to parameterize the hyperbola. Here we've got to be a little bit careful because secant and tangent have vertical asymptotes. So we want to think very carefully about what the interval for t will be here. So secant t, if you recall, is 1 over cosine t. And tangent t is sine t over cosine t. So we won't have any problems unless our denominator is 0. So we want to ask the question, where is cosine t 0? And this happens when t is negative pi over 2, pi over 2, 3 pi over 2, 5 pi over 2, and so on, as well as all the negatives. So we might say that the value that the parameter takes on is going to have some jumps. So we're going to go from negative pi over 2 to pi over 2. That'll give us 1/2 of the hyperbola, and then again from pi over 2 to 3 pi over 2. This is probably more than you're going to need to worry about for the purposes of this class, but those are the basic types of curves that you might be asked to parameterize.